there are three approaches to process large graphs. First is to just design. First one is just to design faster algorithms. Okay, so ideally, we want the algorithm to run in time almost linear in the number of edges. So m to the 1 plus little 1. That's what I mean by almost linear. A little 1 can hide something. That's important. But the most important thing is it's smaller than n squared. So sometimes m can be smaller than n squared is not as simplified. And some famous examples, some success has been already achieved in this direction. For example, in this next flow paper here last year, the next paper at Fox 2022. Okay. And also very recently, all pair mean cuts in next flow. You can just compute all of them in almost linear time. This is the desirable runtime. Okay. And this is for cut and flow. And also for distance, we have the flow algorithm for computing single source for the cuts. Let's take a source and compute perform a PFS, get a short path from this source to all other vertices. Okay. And there are some other problems which these researchers for now believe that cannot be solved in subcubic time. It's an all pair of times. Basically, the all pair version of distances. All pair version of mean cut and net flow can be solved, but it's not true for all pair short paths. Actually, some people believe that below n cubed time we cannot solve this. There are some conjectures. Okay, so the first approach, designing fast algorithms and their problems, which we believe is not solved. And the second approach is to study this graph in modern computation models. The underlying reason is that we have many computers, we have more powerful computing machines. So why don't we just distribute parts of the graph to different machines and let them perform computation simultaneously while talking to each other? And this is exactly what has been doing in distributed parallel models. Okay, and there are also some other models. For example, if you view the graph as being given to us in a stream of edges and vertices, then if we have unbounded running time, the bounded space, then it's like streaming. The other way around, we have unbounded space and bounded running time. So those are very interesting models, and there are many results to models. So there's a third model, which is the model that I like most. Third approach. It's by compression. So the underlying observation is, although the graph is large, the number of vertices of interest to us can be very few. Okay, so for example, if you live in this town, then maybe the locations you care about are just your apartments, this apartment, some other buildings, some favorite restaurants, and train station. A total of 10 locations over million nodes. So why do you need to perform graph computations on the whole graph every time? Okay, so and this is exactly where the graph compression can help us with this. So the compression, the goal is to take the input graph together with those vertices of interest, those we call terminals. Okay, so take the large input graph with a set of terminals, compress it into a smaller graph, containing those terminals, there's red vertices of terminals, while preserving important information spot. Okay, and now if you get this compression, you can run whatever your algorithm on this small graph, and that will be very efficient. Because number of vertices here is already very simple. N cubed, N fourths, how large the polynomial is going to be efficient. So that's what graph compression does. So ideally, we want the information to be preserved as accurate as possible, and we want the graph, the sparsifiers, to be as small as possible. And therefore, there's a trade-off. So normally, we cannot achieve the most reliable. And one of the most important information we want to preserve is our cut, flow, and distance. And today, we're going to see one of them, flow sparsifier. It's usually defined together with cut sparsifier, as they are very similar naturally. So what is the definition of a flow sparsifier? Let's first look at the cut sparsifier. We say a small graph H is a cut sparsifier for a large graph G with respect to a set of terminals. Those are, we always care about those terminals. We always take T with us when we do graph compression. Okay. If and only for every partition of the terminals into the two subsets, the mean cut separating them in the original graph G is about the same as the mean cut separating them in new graph H. For every partition. Okay. About the same, by that I mean we will see a factor Q. Ideally, Q is what? Exactly preserved. But we allow some distortion. It can be some larger than one, even small polynomial, small function depending on K. Okay. So this is the definition of cut sparsifier. The full sparsifier, the definition is a little bit more complicated, but it's natural. If you look at this definition for a few minutes, you'll sort of feel it's more naturally defined. It's just a little bit complicated. We try to define for you. So it says for every demand on a set of terms, the mean congestion of routing that demand in the original graph is about the same as the mean congestion of routing that demands in your sparsifier. Okay. So that's also over. What is a demand? The demand is just I want to route 1 unit from here to here, 2 from here to here, 3 from here to here, 4 from here. This is just a demand. Okay. And what is a flow of routing the demand? It's really a flow that sends 1 unit from here to here, 2 from here, 3, 4. It's a flow. Okay. So what is the congestion of routing the demand? It is intuitively the capacity of the graph for routing this demand. So specifically, it's the inflation, it's the amount of inflation we must do to our edges to accommodate such a flow. Okay, so if you route 1 from here to here, but all your edges have capacity 0.1, the connection is 10. You have to inflate every edge capacity by 10 for such a route, for such a flow to be accommodated, to accommodate such a flow. Okay, is that the definition of congestion here? So if you have low capacity in your edges, the congestion of routing such a flow, such a demand is high. If you have high capacity, then the congestion is low. But either it's high or low, we want to preserve. So this is the definition of flow sparsifier. Is this definition clear? It's sort of the object we are looking at. Yeah. Okay. So ideally, we want the Q to be as small as possible, and the sparsifier to be as small as possible. That's the small is the better learning time we get. The algorithms to do that later. So the research focuses the size quality trade-off here. Okay, the quality is less than Q.
So Zihan, if you also look at routing time, right, the fundamental quantity is congestion plus the length of the longest flow path.
Yeah.
That's a lower bound and upper bound within a constant factor. Can that be accommodated as well in your favor? Can you approximate that notion? Congestion plus length of the flow path?
Yeah. So I think not in this work, but recently there's another notion called hop constraint expanded integration. That's directly shooting for preserving.
And can you do them together, basically?
Yeah, so I think it's sort of different there. So as you will see, our results concerns very high Q rate, 1+, and there for now we do not know how to get better polynomial.
So if you combine, for example, trigger you when we get polynomial, perhaps.
Yeah, not sure. Yeah, I think it's a generalization of spiral computing, not so true. So yeah, I think it has a more general trade-off between the hot slack and the congestion slack. So you can do log both, and you can do better in one, do worse in the other. As as this part of it. But it's sort of fundamentally different from what we're talking about here. That's very interesting. It's sort of what is being meant in the optimized in the distributed congestion plus damage. Here it's just a measure. And it's not sure how to define dilation when your graph is completely irrelevant version of the compute this from stretch. Start using this on. So the research focuses the size and the quality trade-off here. And what is known in this trade-off? So previous work, only the two extreme setting were studied. First extreme setting is the bottom row. It's where the vertices are only terminals. So it's required that the graph you construct, it can only contain terminals, no other vertices at all. So in this case, it's initiated by Andoni and by a sequence of paper. They show that for both flow and cost sparsifiers, best quality achieved in this scenario is between log P over log of P and square root of log. Okay, so T is number of terminals. So there's still a gap here, which I've been trying to close, but not yet. But the main method here is super constant, not yet constant in this case. Okay. And the other extreme scenario is the closed left closed one, which is we require the quantity to be 1. So we require the information to be preserved accurately. Okay. And how many vertices do we need in this case? In this case, that's where the cuts and flow results are separated. Okay. For cut sparsifier, we know that the upper bound to the T and lower bound to the T. So it's bounded within this area between double exponential and single. And for closed sparsifier, very recent work by Krauthgamer and Mosenzon shows that even for 6-terminal network, there exists a 6-terminal network such that exact closed sparsifier require infinite size. So what does infinite size mean? Here, infinite means infinite with respect to terminals. So there's no function that only depends on terminals that can serve as an upper bound on the side. Your size have to be depends on the original graph, log n into 0.1. So these are the previous results. And between that two extreme case, the area here are wide open. Okay. So basically nothing so. So our work can be viewed as trying to step in this area for the first time. What we prove is that even if we allow 1+ε error approximation, we can still prove infinite lower bound just as a closed bound. Okay. So that means if you want some finite bound here, it has to be bounded away from 1.01. This is our result. So actually, the previous work by Andoni, Gupta, and Krauthgamer, they tried to design the data structure for trying to preserve all flows, and they established a framework of constructing flow sparsifier. And what we are showing is really just unfortunately their framework does not give us finite. And in fact, it's likely that there's no finite. So there's a start there. I'll get that. Okay. So this is our main result, and there's also some other results on tensor graphs. Tensor graph is one of the most important special families of graphs. Okay, so we made some kind of more just to have broad network tensor graph. I want to start about that. So for tensor graphs, the previous work showed that for exact cut sparsifier, we can get to the T and over this. Okay, upper and lower bound are both this closed. Okay. So for general case, it is not known, but what we can show is this intersection condition. We allow 1+ε on very small error, but we achieve almost a minimum of this condition. But this is not within the solving. Okay, that's what you mentioned here. Yeah, for general graph, it's wide open, even this intersection is not ruled out. That's about the results. Okay. So it is a picture for now here. I will immediately get to the point where star is.
But for the infinity result, so if you incorporate some weak dependence on n, what's the actual? Is there an upper bound known that's f of p times log n or something?
Yeah. So our result shows omega log n, but I think our result can generalize omega n to the 1/3 or square root. So it's going to be very high. So we didn't try to optimize. So our results immediately as log n. So yeah, what does star mean there? So what is a natural way of constructing flow sparsifier? So one natural way is called contraction, and it is actually the actually the approach adopted by most previous algorithmic results. So what is contraction? It's just partition the graph into a bunch of clusters and contract each cluster into a supernode. That's it. And output the whole result graph. This is the part. Okay, so it's very intuitive. There are some advantages of this approach. For example, you really look at the graph, you really explore the graph structure, and it's intuitive. So it's sort of it's intuitive, like it's really coming from we are sparsifier. And also, eventually, we want to prove that the sparsifier is a flow sparsifier. So the congestion of log any event is upper bounded by something and lower bounded by something. So we want to prove two directions. And this contraction is essentially adding infinite capacity edges between the set of vertices you are contracting. So really sort of increasing capacities. So that means it's only increasing the capacity of routing demands, so that the congestion may only go down for any demands. So we now only need to show that how much it can go down. So it's like two directions. We want to prove, but one direction is originally automatically true if we adopt this approach. So that's probably why this is the most useful approach for constructing a sparsifier. So this is what contraction-based sparsifier looks like. Architecting and contracting. Note that terminals cannot be contracted. They are distinct sides.
So you don't inherit the sort of boundary interactions through capacities on the edges.
Yeah, we do. So yeah, wherever the edge, there's a net connecting to different parts. Otherwise we can add whatever edge is not really one automatically true direction to another. So this is contraction. But our result is actually for contraction-based sparsifiers, 5-terminal network we can get finite value, 6-terminal network we can get even lower values. What it means. For every epsilon, for every 5-terminal network, we can construct a contraction-based flow sparsifier with size depending only on epsilon. It's a size depending on 5 and epsilon. 5 is constant, so only epsilon. And there exists 6-terminal network, such that for any given n, I can construct a graph. This graph, the size n contraction-based flow sparsifier, has to have quality bounded away from 1. This is what we really mean by infinite lower bounds. Even any finite bound, I'm showing you that cannot get full bounds. And this bounded away from 1, its exact value is 10 to the minus 18. We didn't try to optimize, but it's absolute constant.
Okay. For the previous work on exact flow sparsifiers, was it not? Is it not known already that 5-terminal networks have
Yeah, so 5-terminal exact network, not 4-terminal exact network is not. Yeah.
So what is known about networks that have 1 through 5 terminals? Usually.
Yeah, so 1 through 4 terminals, exact flow sparsifiers, on its size, it's pretty very small, something less than 10. 5 terminals, not known, exact or 1+. Yeah, and
So-
6 terminals, no.
So for exact, you need one that is 1.
Here's one. So this is the sharp distinction between 5 terminals. So we have shown. That's more contraction-based. It's our new results. So although this is like 2 different results, one is algorithmic, the other one is lower bound. But really, there's just one line of reasoning, and at the end it branches. So we immediately get to the results. So there's only one line. Is there other questions on the result? Or how do I know if there's any question from the chat?
and like
Okay. Okay. Now I'm going to dive into the details of the proof of results. Okay. So actually, what is the congestion of walking a demand? It's sort of being defined in a very complicated way, but it can be actually computed by a linear program. Okay. So recall that the definition is how much we have to inflate the capacity in order to accommodate certain volume. It's equivalent to say that what fraction of the demand can be route. Have to inflate by 3 times. That means we can route 1/3 of it without inflating. Okay? And that is the lambda, maximizing the fraction. Okay? This is for every pair of terminals, we are going to send lambda fraction of the demand between them via flows, without flows. And the flows cannot violate capacity constraint. So this is just a LP for computing the maximum lambda. So in fact, the congestion is 1 over lambda, minimizing congestion that's not fraction. Okay. What we do is take a look at this view. Okay, I'm going to getting the view is a standard process. I'm going to not show you the process, but intuitively, the primal is maximizing some L infinity norm of a vector, and view is minimizing the L1 vector. This is exactly what I look at. L1 norm. That is maximizing. But what we will do next is take this LP to solve it, and sort of run the solution to a contraction-based. Small size contraction-based for both sides. We'll see what we need. So basically, we only write the primal and take the given and then forget about the primal. We look at the given and then show how to get small size based solution. How are we going to do that? Let's look at the view in more details. So there are two types of variables, delta variables and L variables. For each L, we can think of them as giving a length. We can first make a simplification that we can assume all the CI are one. Assume that it's just unweighted graph. Because even if it's weighted, general weighted, we can think of them as parallel edges. So it's essentially no difference. Okay, so we can ignore this first. And then look at variables. For each L, it's really just setting up a length of each edge. Okay, so if you write down some of LP and take the view, you know that the primal, if it is some flow, then the view variables have the length, have the meaning of length. And this is the case here too. LE is we assign a length variable. And delta, what is delta? The only connection between delta and LE is this connection. So what is saying, for every pair of terminals, and for every path connecting this pair of terminals, the total length on the edges of this path is at least delta between them. What this is saying is delta is the shortest path distance in the graph where the edges are weighted by elements. Okay. The distance, any path is total length this distance. Okay. This is the meaning of two variables, two types of variables, and there's another constraint, which is the first one. It's a little bit hard to manage to understand, but we can think of now as some type of average distance is larger than first. Average distance larger. Okay, so this is what the variable means, length distance. Okay. How do we get contraction-based sparsifier out of that? So what we can do is solve this and get LEs and deltas. We need to get a sparsifier out. So what is a sparsifier? Contraction-based flow sparsifier is really partitioning the graph into clusters and contracting each part in the supernode. So it's really partitioning and contraction. So what should we do? To a lot of lengths and edges, we can basically manipulate these lengths and edges. What should we do? Make it look like that clusters are being contracted. We need to do something to the length, make it look like the clusters are being contracted. And the things to do here is to give zero lengths to edges within the cluster, and to give non-zero lengths to edges outside of the cluster. So this is what we're going to do. We're going to get a solution here. It's intuitively a fractional solution, but it's really just the edge length. And round them, manipulate the edge length and distances, so that it's really giving us a partition in the sense that the edge within each part is zero, and edge between different parts. Okay. And we also need to be a physical solution of this LP, so that it's really still optimizing LP in the subjective constraint. So the only constraint apart from that is the first, every distance is some every distance larger than something. Now we still want this to be both, so every distance still larger than something. But as it's hard to understand, hard to memorize in the first place, we might want to ensure something stronger. Something stronger, what we can do is we can try to ensure that the distance between every pair of terminals do not decrease. So if originally this is satisfied, after manipulating, if we ensure delta doesn't decrease, any delta doesn't, then this constraint is still satisfied. This is something that we can do, and this is indeed something stronger. But we can see how well we are trying to achieve that. And these are the input values, so they are just a constant. So whatever delta, they just go up in this person. And we still want that objective solution to not blow up to larger contraction. This is a way of just making sure that congestion of blocking this single demand. Okay. And we also want that number of clusters is not here. So this is probably already very complicated, and this is even for routing one event. A lot of remember about the two different. But let me ease your mind, ease your mind with the form in this one. And then we have the basket. That's shown in the first slide. So they say that if you want a 1+epsilon approximate, we do not really consider an infinite continuum of events. There's only a finite set of events. And actually, just by considering each one of them, you can deal with each one of them well, then we can deal with. So what they show is that if factor Q here can be achieved by set T here for a single event, then the factor Q times 1+epsilon can be achieved with some function with size bounded by some function depending on only T. T is normal terms. So all we need is this bounds does not depend on n. It can depend on T and epsilon. This is how we want. So if P is only a function of K and epsilon, this is also a function only of K and epsilon. Maybe it's very horrible looking, it's very terrifying, but it's finite. In our sense, finite is clear. Okay. So really what we need to do is just look at this. We try to achieve this for one event. They tell us they have the rest. Just look at what it is. Okay. So actually this problem is sort of a generalization of one previously extensively studied problem, which is called zero extension. So in the zero extension, we are given a set of terminals. And it's a special case of our problem here because they only want a partitioning into T parts. So we call that the extreme case is vertices are just a T. No other standard vertices at all. So each part contains a terminal, and each terminal between belongs to a part. No more other redundant parts. Okay. They partition this into T parts and try to minimize this ratio. So our ratio is also just an objective function. Do not go up by factor Q, but it's also minimizing the ratio. The new sum over the old sum divided by Q is a factor. Okay, so all the previous work of this extreme setting, they are indeed obtained by looking at this space. And they show that in this special case, the best ratio they can get is between square root of log n, square root of log t and log t or log t. This is our previous one. And what we are trying to do is to consider a standard version. So we allow standard vertices, by which in the statement, the problem we allow partitions into more than T parts. We allow into P parts. T can be any function between T and S. And we also allow ourselves to manipulate the metric such that the terminal distance does not increase if we still want to maintain that average distance more. So this is usually the term. The terminal distance does not increase. And we are still minimizing the same ratio in all of the Q. Okay. So this is just our relation with the spectrum. They study this version, we are studying the standard version. And actually we should for 1+epsilon problem. Recall that Q give us Q times 1+epsilon. And we want Q 1+epsilon. As a result, we want really to study Q equals 1 case. So we want Q times 1+epsilon, we want Q is 1. So we really want that the new sum is less than the ratio. So this is all we want to achieve. Okay, so let's recall. We are given an LP by solving which we get a lot of lengths and distances. We are allowed to manipulate edge lengths so that the terminal distance do not decrease. But what we care about is the total length of all edges. They do not increase. This is a problem. Yeah, sum of all the lengths that they did are for 1. Sum of all lengths of the ends.
So is it why we choose to minimize this fraction on the next slide?
Okay, so it's like we want to take the solution, we want to solve this LP, take this solution, want to transfer it into a solution that reflects the partition. It has to be still a feasible solution of this LP. Only it has 0 on a lot of edges and non-zero between different parts. Okay? And we still want it to be a feasible solution of this. So, and the objective does not go up by a lot. That is the meaning of preserving the congestion overall. It is extracted as a primal LP. Take the view to construct another new feasible solution without increasing the objective by a lot. That's using our minutes. The meaning of preserving the congestion overall. Maybe a little bit not very immediate. Statue is nothing. So our problem in here. Give a graph is actually
Alright, why do we need Q equals one? Why don't we take Q equals one plus epsilon?
yeah, that's good catch. So eventually it makes no difference. For 5 we can achieve 1. For 6 we can rule out 1 plus 1 plus. You can if you are burdened by too much memory, then this is the only statement you want to look at again. And so we are given a graph with edge lenses, a set of terminal in it. So we want to partition it into P parts by giving new edge lenses to the edges, such that the terminal distance does not increase, and the total edge length does not increase. That's what we're doing. Okay, so from now on, we will just focus on this one. We will start from 2 terminal case, and then look at 3, 4, 5, 6. Eventually, we will see this fundamental 5, 6. That's good. Yeah. Okay. So let's first look at the special case where there are just 2 terminals. What should we do in this case? How should we partition the graph? A direct approach, also a straightforward approach, is just to compute a mean cut and contract graph as whatever lies on the left, contract it to T1. Whatever lies on the right, contract it to T2. I'll take a graph like this. That's 2 terminals with a lot of parallel edges. How many parallel edges mean cut? That's all the edges we have to maintain. And we need to give edges new lenses. The length we give to every edge is the distance we will already from. Because we do not want to destroy their distance. We cannot shrink. So the cost we're getting, the sum of total length is mean cut times distance. This is actually good because we can prove that in the original graph, the total edge length is at least this much. Why is that? Let me see why original graph the total edge length. Well, actually, by the mean cut, that's all 0. If you can route, if the mean cut is C here, then there exists edge destroyed passes from T1 to T2. C many mean cut many edge destroyed passes. And they use completely 0 set of edges. And each pass, the total length is at least distance between T1 and T2. So just looking at these edges, each of them contributes this much. And there are how many total mean cut? Right, that's the mean cut. Need 1 more or 2 more lines. That's the simple solution to points. So this is a special case. We may want to be a little more flexible. But by the way, that also means for 2 terminal case, we just need 2 parts. We can contract the graph into 2 without any standard errors. Let's be more flexible in this case. In the sense, we can consider another special case in the 2 terminal case. Let's consider that the graph, all vertices of the graph lies on some shortest path. There can be other edges connecting parallel, and we do not care about them. There exists a shortest path going through all the other vertices. Here, we still want to solve the problem. We can definitely do as the last slide shows, just compute a mean cut, left to right. But we want to be more flexible here. Actually, a more flexible solution is we can pick an edge in the shortest path with probability proportional to its length and produce this random threshold. I suppose it's a very commonly used technique in drawing. when you have an interval, pick a random number, you will randomly compile. This is exactly what happened here. So random pick an edge proportional to its probability, whatever lies on the left of it, keep on. Whatever lies on the right of it, that's the contraction we're going to compute. So what is the total new edge length? Okay, for whatever edge, if they are separated, meaning the endpoints are one going to T1, the other going to T2, they will be given the new edge length distance T1 and T2. This will be their new edge length. We're going to exactly given before. Okay, but what is the probability of an edge being separated? It is the probability that we select one of these edges in the shortest path. So the probability is the distance on path over the whole length. The probability of this edge being separated. And if they are separated, they will be given this. They will be given this. So this is expected units. Okay. And as this is the shortest path, this edge, the real length must be at least this long. And this is the shortest path. Okay. So it's going to be bounded by edge length over the sides. It's sort of simple analysis. What's really happening here is you take a random threshold count, then any edge, expect a new length is bounded by its own length. Like rounding. Another way to look at this is it has a name. Sort of a metric specify this expected length bounded by its own length is sometimes called decomposable. So what really happens here is L1 metric or line metric is decomposable. That is all. Back to new lengths. Okay. So this is case 2. This is case T2. And we will see that how the sequence for 3, 4, 5, 6. Okay. So for 3 vertex case, 3 terminal case, things become fundamentally different. Ready? Okay. Let's see an example here. So we recall we want to decrease the total edge length. So we want to make sure that total length has not increase. And the terminal distance without total edge length will not increase. So what should we do to this example? Okay. So in this example, ABC are terminals. First observation is all the shortest passes are supported by P. So AC is 5. AB is 7. BC is 8. All goes through P. And Q does not support any terminals. So this 8 is larger than 7. Okay, the first observation is we may not want to touch P, as we do not want to distort the distance between terminals. Okay, so if we decrease this by delta, then we have to increase this and this by delta to not destroy their distance. So that's -1 delta but +2 delta. This small less. It's increasing the potential. Okay, first observation, we do not want to touch. Well, we can definitely do a lot of things to Q, as it's not supporting any short paths. So it's some regionally for us. Okay. So if we decrease this 4 to 5 and this 4 to 3, 6 to 5, then it's not still not violating any distance. Okay, so now Q now supports some short paths. Now this 3 plus 4 is another 7 between A and B. Okay, this 3 and 5 is another 8 between B and C. So it now supports. And we cannot further suppress any. We can suppress this, but no further. Okay, this is some first step simplification. And if you look at the resulting picture, if you look at this picture, viewing this as 3 and viewing this 5, Q can be identified with a point lying on the PB segment. Q is essentially here. Okay, if you look at the distances, this is 3. Okay, this is 5. 2 plus 3 is 5. That's 4. 2 plus 2 is 4. So essentially, we should be making the first simplification and get something like this, and then work with this. And this, this example is not an exception. What we can show is that no matter what graph we're given to me at the beginning, I can construct a skeleton like this. And this skeleton is just a 3 passes with length depending on only the distance, terminal distance. It does not depend on the graph structure. Okay. So this length, this segment has length AC distance plus BC minus AD. And this has this can check and sum. For these two segments, there is a distance DC. So this is cancelled out. I can construct a structure like this. And moreover, I can project all the vertices in the orbital graph to some point in this structure, just like what we have done to Q. It was projected. We can project whatever vertices in the orbital graph to the structure, such that every edge, the length only decrease. That's what we can do. And then what remains is we can see what all the points are on this structure, on this skeleton. And we just need to partition the skeleton. The skeleton is sort of similar to what we have done in the special case of two terminals. We just random cut here, random cut here, random cut here. So this is how we do this three terminals. Eventually, we can have 1, 2, 3, 4 terminals, 4 vertices. Okay, so let's try to make this plan more concrete. This structure actually has a name. We solved it. But it appears that it appears in some math literature like the 1980s. And it has a name called type span. So this structure with respect to that metric, but not depending on the graph, but the metric. This structure is called a type span. So what we are really doing is take the input graph with edge weights, project it into the type span, and then partition type span. That's how we just want to show that type span have been composed into INM parts, such as and here, what we are saying is we just need 4 parts. Okay. Random parts here, random parts here, random parts here. Whatever is lying on this side of the random parts goes into the P3 equals. Okay. So this type span is the only technical definition we want to take something away of this topic. Let's look at it after we getting a better understanding of what type span is. Equals 4, 5, 6 case become bigger than 7. Okay, so now I'm going into the definition of type span. So ideally, type span is a result of vectors that we cannot suppress. Okay, so what we have done to Q is suppress this distance to terminals until we cannot do so. Type span contains all points that we cannot further suppress. Okay. So the input is a metric, and type span is represented as k dimensional vectors. Okay, so the metric is on k terminals, k point metric, and it will be great to think of the k dimensional vectors as imaginary points in this. So the metric only contains k points, but I want to imagine there are many other points in the metric, and how to represent them. This vector represents a point that is at distance for each I, xi, to the terminal I. If I get vector 1, 1, 1, 1, then I have an imaginary point at distance 1 to each terminal. I imagine this. So, for it to be lying in the type span, it has to be that we cannot further depress, we cannot further suppress any of its distance. So, 2 things to present. First, all triangle inequalities need to be respected. And second, for each I, there has to be some inequality that's already packed. And it is this type inequality preventing us from further suppressing that. Okay. So please go to 10 seconds to look at this definition. So it's k-dimensional vectors, all triangle inequalities are satisfied. And for each coordinate, some inequality related to this coordinate is already cut. So let's see an example on 3 objects. Let's see the old metric here. 5, 7, 8. How many inequalities per se? Inequality is just for 3-dimensional vectors, 2 of them is larger than the distance between inequalities. So there are 3 constraints. A plus C larger than 5. A plus B larger than 7. A means XA. And there are 3 constraints. So for each I, some inequality has to be cut. There are just in total 3 inequalities. So one is concerning AB, the other BC, and the other AC. If we want for each coordinate some inequality is cut, we have to pick 2 of them. So Actually, the time span just looks like this. And let's see how it's going. We start with terminals, and their corresponding vector. It is 0, 7, 5, meaning it is at distance 0 from A, at distance 7 from B, which is it is a 5 from B. It's representing A. Okay. So we have to choose two inequalities to impact. That's with a loss of general independence. That's where AB and BC impact. So what we can do is we have three-dimensional vector, but two type constraints. There's one degree of freedom that we can do this action. That is increasing the distance to A and decreasing distance to B and C at the same rate to make sure that AB and AC stays tight. Okay, so what we can do is we go 1 and get 1, 6, 4. If we go 2, we're at 2, 5, 3, which is exactly at this point. And right now, it's all constraints are being met, so we cannot further increase their distance. Otherwise, this 5 and 3 will both go down and violate the state. Okay, this is how this type span is going. Okay, and what we are really doing is keep AB and AC tight. And the only thing we can do is plus minus minus. Get this point. We do the exactly same for the two other terminals, and they land at the same middle point. This is most of our can work out. Okay, so this is what our type span is being constructed. So this is probably not a rigorous truth, but I hope to give you some vision of what it is. Okay, so for the three-dimensional case, what we are doing next is random path, random path, random path. Now looking for parts. Okay, so in the meantime, we will be looking at what the type span structure is for the 6, for the 4, 5, and 6. Okay. So is there any questions on the type span? Any part you want to explain before? Okay, so 4 points. What is the type span for 4-point matrix? So that's it, that is how 4-point. I'm not going to that level of details again, but we still push points away from one terminal until we have this 3.5 or 4.5 or 8 start. And we do the same for every point when we get a structure like this. Unfortunately, we do not get a common center point. That's only a privilege for switching. But we will get some structure like this. It's a square with like this to be distance to this to be the distance to the diagonals in 5. It has to be this case. The 5 needs to be the sum of 2 s. But what happens here is that this is actually a 2-dimension type span space. So from this point, we cannot further increase the distance to it and decrease the distance to others. But what we can do is increase the distance to it and this and decrease the distance from this point to this two. So increase 2 coordinates and decrease the other 2. Plus, plus, minus, minus instead of plus, minus. This is what we can do. And essentially, we can do this for every point here. Because the area here, all points in this type span, what are the type inequalities? It's this inequality and this inequality. So it's okay. So there are 2 degrees of freedom, 4 coordinates, 2 constraints. We can increase to a degree the other. Eventually, the intuition is they will give us a 2-dimensional area in the type span. And luckily, that 2-dimensional area is this L1 norm. Okay, an L1 norm just similar to 1-dimensional. One measure, we do not have the random cut here, random cut here. The whole thing is the part we do 4 7 node plus 4 terminal plus P4 of 8. It's just how we do for it. The one thing, one catch here is just a 4-terminal case. There are 2-dimensional regions in the type span. But luckily, they are still equipped with 1. We finally get to 5 and 6. 5, and guess how large it is. For one cases, we need 8 parts. And I will copy with the closest gap. Yes.
15.
15, the other is.
10.
You are quite optimistic. Yeah, so it's 1, 2. So I think, yeah, but the time span looks much more complicated. It's still, the lucky thing is still consists of 1-dimensional and 2-dimensional areas. Only it's much more entangled with each other. So 4 terminals is 4 tails with a square domain. Now the 2-dimensional areas are entangled. These 2 shares alike. These 2 shares alike. Okay, there are actually 3 types of time spans. This is the first, this is the second. The third one is similar to the second. I'm not showing you. Okay. So this is really 5 2-dimensional spaces entangled with each other. The lucky thing is they are still 2-dimensional and L1, and we do not know how to do with L1. We just need to be more careful. We cannot do independent random striking cut. We need to do random sort, pick a random vertex here and do a cut here and extend it to both these 2 areas. And we will take 5 random points on each side, and they will give us naturally a way separating this area. Does that make sense? I know it's already not a rigorous explanation, but random cuts are now dependent. It's not completely dependent area. Okay, so let me a point here to give equation here. Some points are used twice, like consecutive, I guess. Okay, and there are some other types of time spans. Now, one piece of paper is not enough to comment. So it's really a piece of paper, and there's an angle standing out of that. It can be viewed as the downside or upside, representing different combination of 4 time spans. The downside is like this for sub-time span. If the upside, then they represent the sub-time span of the background. Intuitively, it's still 2-dimensional. That's the only thing we can still do packages. Only the random cut here is a little more complicated. So we will select random vertex here and do this random cut, and then this random along this 2 lines. That's the point. But still random cuts, just more entangled. Okay, this is the 5 terminal case, and after the contents and 2. Suppose it roll factorial, even more than its function. Okay. Last thing about 6 terminal is that it's no longer 2-dimensional, and it's at least 3-dimensional. That's why we cannot both get same random cut. 3-dimensional means non-decomposable, and turn it into a lower bound for the whole problem is very technical. To serve out. I try to give you an intuition why it's fundamentally different from. So why it's 3-dimensional? If we look at a subset of 5 terminals, we like to look at this 5, then this will be the aspect. Piece of paper with us with an angle standing up. We look at this 5, then it's going to be this aspect. But we have to accommodate everything, so eventually we have to accommodate the whole body. That becomes 3-dimensional. As 3-dimensional is not decomposable, we cannot really find cuts that are also with each other and cuts with random. So I do not have a very good intuition on why 3-dimensional is not L1, but I can try to give you a vague explanation. Okay, so for 2-dimensional, the L infinity ball. Okay, so there is something related to L infinity here. Sure, you notice. So when we do 0, 7, 5, push it down here, increasing that by 1, decreasing 2 by 1. We're really considering points that are at distance L infinity distance 1 from it. Increasing 1 by 1. That's really moving along the geodesic directions with respect to L infinity. So increasing something, decreasing something simultaneously. It's sure to get that. So that's sort of the way of constructing tight spans is moving along L infinities of directions. And for 2-dimensional, L infinity, the unit ball is a square. The L1 unit ball is also a square, only rotated, but they are all the same structure. That's why L2, the two-dimensional L1 can be viewed as, the two-dimensional L infinity can be viewed as L1. They are really the same shape, only rotating. Now for three-dimensional, if you think that L1, L infinity ball is a cube, three-dimensional L infinity ball is a cube. A three-dimensional L1 ball is 1 point, 4 point, 1 point, like a concatenation of two pyramids. It's a 6-terminal, 6-point polygon versus a 8-point polygon. Therefore, no different. And I hope that convinces you to some light extent that three-dimensional case, this is not the same. So that's all for the results, the second part. So if you look at the roadmap is, we want to construct a flow sparsifier, which we want for all demands conditions to be preserved. The previous work by Andoni, Gupta, and Krauthgamer show that we only need to worry about one dimension. They can discretize the demand a little bit by paying overall cost in the size function, but still only determining. Okay, and by LP duality, we can transfer preserving one demand into solving the problem of zero center with the nodes. That is, then you can add lengths, some become zero, some zero. Okay, but also add lengths do not decrease. And after this projection step, we can only consider the zero center with standard node instances that are projected into the time span. We only need to count time span. And the crucial distinction here is that the time span for 5-point matrix is at most 2-dimensional. And 5-point for a 6-terminal matrix is 3-dimensional for most. So that's what the results here are. So that's how we get results. So some open problems here. I think area inside is still wide open, so it would be good to push any of the axes in where they go. But I think the most most interesting problem is if we have to have a finite flow sparsifier, how much can we push the quality? And if we have to have a constant quality, how much in the size? Okay, so that's on the top. Thank you for listening.
Questions? Questions? So you mentioned cut flows and distance path, right? Can you tell us? So what happens with flows and distance? Or what's the best one?
Flow and distance. You want to consider flow or distance?
Yeah, separate.
Okay. So this result, it's all results are flows that so okay, so we go back to
Sorry,
okay. So this is for cut right side. The yellow one is this purple one is for flow. So we consider both flow and cuts. And because the other results here is only for micro. So
distances?
yeah, distance. Okay, so distance is one of the special cases. We can explore it now. It's for n graph. But for general graph, there's a k to the 4 of exact preserve. The k terminals, no matter what the graph is, and there's no structural requirement. It can give you a k to the 4 values. New graph preserve all pairwise distance. The algorithm is for every pair of terminals, take its shortest path in the original graph. Now, two shortest paths must each ones goes along together for a while and departs, giving us two special vertices. So k² paths, k4 pairs of pairs, k to the 4 special vertices. That is what we know, and the lower bound is k², which is the degree of freedom we need at least to accommodate those changes. So this is for example.
Approximate, what is one?
Yes. So previous work on approximate 1+ε on planar graphs, we can achieve near linear size to the same intersection here. The approach for proving this is actually similar to for proving distance. not aware of others. Suppose this will be generalizable to student management, 1+, maybe, but then not sure.
Expanders and so on also should be good.
Yeah, expander, like how many terms do you want? Like expander on n vertices, how many of them is yeah, I think it's tricky. If you pick too few, it loses the control. Too many, then itself is already a good. We cannot do that already.
And then you and I spoke about electrical resistance. You said not necessary.
Yeah, this I didn't do a very good research on. I think for exact preserving, they have a case where it's already upper low bound close. It's the desirable. That's probably by short copy. This I'm not familiar with. It's some algebraic. That's already very good. And I suppose they can do 1+. This short complement. I think it's a very recent. Short complement is a operation with the matrix. Take some parts out. Yeah, I do not know which paper that originally. It should be known.
So in the motivation you mentioned, like you want to use sparsifier to process and run algorithms on large graphs. So how does this running time fit into the motivation?
So the constructing a sparsifier may takes a long time, like solving an LP or looking at the structure. But the idea is this is a one-shot thing. Any demands you want to add, or you want to figure out this convention, you never run on this. So I think for at least for this panel case, there are indeed concrete applications of really using this operating and stuff and speed up the running time. For a general graph, it's not used.
Do you know like just about where is the turning point between using a like classical traditional algorithm versus using a sparsifier?
Okay, so I think for polynomial quality, if you allow the transformation ratio to be as large as polynomial, then there are more efficient, simpler construction than this. Like tree flow sparsifier, ranking tree, obtained by a sequence of accommodation. That is much better, and maybe the construction itself is also very efficient. This concerns very high quality regime. And maybe concept is also that approach loses too much barriers.
Good questions. Thanks again.